Hi, everyone. Welcome to the Learning Curve, Scale AI's monthly Tech Talk series. Today's topic is on how we scale data labeling with machine learning, and our presenter is Felix Lau, a research engineer on the machine learning team here at Scale. Before we begin, just a quick housekeeping note. We'll have Q&A after the presentation, but if you have any questions as we go through the presentation, please submit them using the Q&A feature of the Zoom. And with that, Felix, please go ahead and take it away.
Hello, everyone. Thanks for tuning in again. My name is Felix Lau. I'm a research engineer from the machine learning team. Today's topic is scaling data labeling with machine learning. So in this talk, I will go through the use cases of machine learning in data labeling, the challenges and approaches to train model on heterogeneous data sets, and finally, continual learning, fine-tuning a model as new annotated data becomes available. Let's start with the use cases of machine learning in data labeling. To give you some background, Scale provides an API for annotation. Our customer makes a HTTP request specifying the objects that they want to annotate, the instructions, the image, video, or point cloud. We then send a callback with the ground truth annotation. We use machine learning model in multiple places in our pipeline to increase the quality and the speed of our annotation. Let me tell you some concrete use cases of machine learning in data labeling. So first, in the top left is pre-labeling. In this example, you can see a point cloud bounding box task. We provide high confidence detection outputs to our labeler such that our labelers only need to modify the model outputs and correct any mistakes instead of annotating the point cloud from scratch. Second, in the bottom left is active tooling. Labeler can work with the intermediate outputs of the model to speed up annotation. For example, in semantic segmentation, we provide labelers superpixels, which group similar pixels together so that labelers don't have to label each pixel separately and can instead use these superpixels to speed up the annotation process. Lastly, in the right is quality assurance, or what we call linting. Annotating thousands of images every day is a very laborious process, so mistakes are sometimes made. We use machine learning model to detect these errors by looking at the likelihood of the annotation given the image. For example, in this case, the person is missing, but our detection model is very confident that there is indeed a person. Similarly, we can detect that the bounding box is not tight enough. This diagram shows you our overall annotation process, and in every step of this pipeline, we try to use machine learning to enhance the ability of our labelers to increase quality, reduce mistake, and improve the overall speed. Next, I'm going to talk about the challenges and approaches for training across heterogeneous data sets. The images from our customers are very diverse. They have very different background, objects, weather condition, geographic location, day of time, and camera types. For example, in the dataset in the top left is a relatively small town with lots of people. To its right, it's a challenging image because it's in nighttime and the image is blurry and overexposed. The image in the bottom left shows a more urban environment with skyscrapers. To its left, we have a more rural environment with unpaved road and very different types of vegetation. In the middle left, we have images that are taken during the winter after a snowstorm, so it's very difficult to see the lane marking. And finally, in the bottom left, we have images from Asia where bicycles are relatively common on road. So, but not only the images are diverse, the objects that our customers want us to annotate are quite diverse as well. We call this label category taxonomy. For example, in the taxonomy of dataset A, pedestrians are categorized into adults and children. But in dataset B, there's only a single category for pedestrian, and only small cars are annotated. In dataset C, all cars are annotated with a single class, and no pedestrians are annotated. So there are a lot of ways to annotate the same image, depending what the taxonomy looks like. Furthermore, having the same label name doesn't mean that the objects can be labeled the same way. For example, in these two images, we show two different annotation styles of the same truck. The one in the left includes the side mirror, while the one on the right does not. Which one is correct depends on the labeling instructions. So without considering this difference in labeling rules, it's very difficult for the model to converge to either annotation style in the left or in the right. Despite these challenges, training across multiple dataset is still a very attractive option because the model gets to train on a lot more data, and that will improve generalization. Most importantly, it eliminates RAM time, which is a period of time where the model accuracy is not good enough to be used in production because there's a lack of data. In this ramp period, we need to wait for more data points to be annotated before we can deploy the models to production. However, if we train across the data sets, there's no such restriction because the model can utilize all the data points from other data sets. Now, I want to talk about the approaches to train on heterogeneous data sets. We will consider the use case of training an object detection model on 2D images. First is a naive yet pretty effective approach where we just train one model per object class that we want to detect. For example, we will collect all the images from pedestrian labeled and train the models to just to predict pedestrian. We repeat this process for the common classes like vehicle or traffic lights. And then at inference time, we'll run all this model at the same time to combine the prediction results. The advantage of this approach is that the model are specialized to do one thing and will not be affected by the distribution change in the label space. For example, for a multi-class detection model that detects both pedestrian and vehicle, when the model is fine-tuned on data on highway, so there's very few pedestrian but lots and lots of vehicle, it's arguably that the performance of pedestrian might be reduced. This naive approach will not have this performance degradation problem because there's a dedicated model for each class. However, there's one big obvious drawback, which is that the images the model are encoding are essentially the same. So even though the objects to be detected are different, the encoders should still be able to share a lot of different common features. Next, we'll look at our approach to train a single detection model across different data sets using what we call a super taxonomy. Here we're showing the taxonomies for 3 different data sets. Despite the differences, there's still lots of commonality which we can extract into the super taxonomy. For example, we can map pedestrian from taxonomy A to person in the super taxonomy, and we can map pedestrian, adult pedestrian, child pedestrian, construction workers, and police officer to the person class in the super taxonomy. We can repeat this process until we have the majority of the dataset labeled taxonomy mapped to the super taxonomy. The drawback of this approach is that it's very difficult to decide how granular the super taxonomy should be. For example, in the super taxonomy, there's no differentiation between different types of pedestrian. But in taxonomy B, the pedestrian class are differentiated. For example, we cannot put child pedestrian class into the super taxonomy because the pedestrians in taxonomy A and C are not differentiated. So therefore, despite the fact that we can train across datasets using a single model, some information is still being lost because of the granularity are different across different dataset taxonomies. Now I want to talk about the loss function we use in this super taxonomy approach. In focal loss or in RetNet, when the IOU of the anchors and the ground truth is between 0.4 and 0.5, depending on the hyperparameters, the gradient of those anchors are zeroed out because these anchors are ambiguous. We took a similar approach when dealing with images that are not completely annotated according to the super taxonomy. For example, in the right, only pedestrian and traffic lights are mapped so that we don't know whether car, bikes, stop sign are actually present in the image or not. So therefore, we can only apply the loss for the classes that we have mapped, that is pedestrian and traffic light, and we do not penalize the model if it detects a car, bikes, or stop sign. Finally, I want to talk about a multitask approach. This approach is like the super taxonomy, where there's a shared backbone, but there's only the classification and box regression output heads per taxonomy. This avoids the problem of making the super taxonomy in the first place. However, balancing the weights of these losses is quite challenging. For example, dataset A could have 10 million images, while dataset C could have only 10,000 images. In this example, the output heads of dataset C might be underfitting because of the imbalance of data volume across datasets. In the end, we will talk about an overall approach that would overcome this problem of balancing between different losses. Now, next, I want to talk about the continual learning, which is to fine-tune the model as newly annotated data becomes available. Typically, a dataset follows a long-tail distribution, where the head of the distribution contains common and easy to learn images, while data scarcity is a problem in the tail. For the head of the image, for the head of the dataset, the objective is to prevent catastrophic forgetting, while in the tail, the problem can be seen as few-shot learning. In scale data, the head of the distribution is usually a car driving down a city street or highway. The middle part of the distribution could be self-driving car in a busy intersection. The tail end of the distribution could contain construction sites and emergency vehicles, which are rare. Arguably, the tail end of the distribution is very important to get right because they represent edge cases. One of the big challenges of continual learning is to deal with distribution shift without forgetting what the network has learned. In this example, we first trained the model with dataset A, which the weather is sunny in urban environment and in daytime. Next month, dataset B has finished the annotation process, and it contains snowy daytime images in rural settings. A few months went by, and we continue to fine-tune this model with images where it is raining and at night. Finally, we start to get back annotation data from dataset A, where it's sunny in the dataset in the image again. It's quite possible in this point, the model will not perform very well on dataset A because the type of images in dataset A, B, C are quite different. Instead of fine-tuning on just the new image, we can also train the model from scratch every time. However, this is not a very practical solution because there are millions of images and this has a huge cost and time implication. So we want to take an approach that does not require us to train the model from scratch every time while being able to deal with distribution shift. Now, I will describe a few approaches to overcome catastrophic forgetting. The first approach are Coreset methods. Coreset methods select a subset of the dataset such that when you train on this smaller subset, the model can still achieve a similar accuracy comparing to being trained on the full dataset. The idea is that when we fine-tune a model, we fine-tune the model with the condensed dataset along with the new dataset. So here are three examples of these Coreset methods. The first method is a baseline method, which is to simply randomly select a subset of data points. The second method is called herding. The idea is to perform clustering on the feature space of the data point and choose the most representative data point according to the cluster center. In practice, this is to simply choose samples closest to the cluster center. Herding is a pretty effective way to learn the head of the distribution because that's where the data is most abundant and where the cluster will fall. The final method is to remove what's called unforgettable samples from the dataset. Unforgettable samples are data points with strictly increasing accuracy during training. It was found that these unforgettable examples has very little to do with the test accuracy of a model, so they can simply be removed from the training set. Inspired by this unforgettable examples idea, we extended to categorize data point into 3 different types: easy, hard, and edge cases. Easy examples are the ones which loss reduce consistently during training. This can be seen as the head of the distribution. The hard examples are ones which the loss reduce a little bit initially, but remain relatively high during training. This usually represents the middle part of the distribution where more training steps or a larger network is required to reduce the training loss. Finally, the edge cases are the data point which the loss remain high or even increases as the model is being trained. These examples usually belong to the tail end of the distribution, where, for example, the object is in a non-typical orientation. With this categorization, we can then undersample the easy data points while oversampling the edge cases and the hard example in the condensed dataset, such that when the fine-tuned model will not forget about these rare examples. I want to talk about another related approach, which is called dataset distillation. Unlike previous approach, which there are real data points in the condensed dataset, dataset distillation synthesizes a small number of data points which do not need to come from the original distribution. And when you train a model on these synthetic examples, the model can still perform approximately the same as on the original data. This approach can be used to quickly fine-tune a pre-trained model on another dataset, such as taking a pre-trained SVHN and fine-tune it on MNIST. This approach is useful when there are dataset privacy constraints where we cannot store the original data. Generating the synthetic example will allow us to train new model despite not having access to the original data sets. By combining the techniques we discussed today about training heterogeneous dataset and continual learning, we come up with this following strategy to prevent catastrophic forgetting while being able to learn on new data. First, we train a multitask common model with the initial data batch. Then we fine-tune this common model on downstream tasks such as pre-labeling, linting, and active tooling. We perform this fine-tuning because we don't want to worry about the weighting between different losses, and it's possible for us to run multiple models in production. Then, when we have a new batch of data, we first condense the initial data batch by looking at how the training loss evolves when we first train the first model in order to oversample hard and edge cases. Then we fine-tune the common model with this new batch of data with the condensed data we made from dataset batch 1. From this new common model, we repeat this process of fine-tuning for downstream tasks such as pre-labeling, linting, and active tooling. So what this strategy allows us to do is to obtain a common model that's trained across all dataset that's continuously being improved while being able to have good performance on downstream tasks and not forgetting the edge cases and hard examples. I hope you get a sense of how machine learning can be applied in data labeling, the challenges and approaches to train on heterogeneous datasets, and how we continuously improve our models using new data. Thank you for listening.
Great. Thank you so much, Felix. All right. We now have some time for Q&A. So again, if you have any questions on what was presented, please go ahead and submit them in the Q&A feature. Just to kick things off, first question I have for you, Felix. You mentioned several different challenges for training models across multiple data sets. Which of them is the most common or most challenging to solve for?
The biggest challenge would be the diversity in labeling rule, because that basically prevents the super taxonomy approach from getting good performance, because we cannot mapping, even the name of the label, which is truck, is the same. We can't actually mapping them to the same label in the super taxonomy would be incorrect because of this different sizing. So that is a pretty big challenge. For the other two challenge, we have discussed some ways to overcome that challenge there. And for challenge 1, the diversity in data domain, there are a lot of literature about domain adaptation to solve this particular problem. So challenge 1 and 2 are relatively well researched, but challenge 3 is relatively new, and more research is needed to overcome that problem.
Great. For solutions to training multiple data sets, can you tell us about which approach you ended up using?
Yeah, so we tried all these approaches, and we first started with approach 1. We actually got pretty good results. And then we went on to approach 2, because we think that by sharing backbone, we could benefit from being trained on more data. But then there is a problem with the granularity of the super taxonomy. So we are now looking at approach 3, which is the multitask, multi-headed approach. But we unfortunately don't have empirical number to show at this moment, but stay tuned. We will be publishing more paper or more blog posts about this.
Great. And why are bounding boxes used as the shape versus something perfectly fitting?
In this example, I'm using bounding box just as an example, but the same idea apply for instance segmentation, which you can get like a pretty good shape that surrounds the objects that you're annotating. This method is not limited to bounding boxes. It's just used as an example.
Great, thank you. There are currently no other questions in the Q&A. We'll give folks another minute here to submit. While we wait, I just wanted to say our next Tech Talk will be on February 17th, where we'll be talking about what's new in our computer vision endpoints. So if you're interested in joining, please make sure to register by going to scale.com/events. Another question here, Felix. How do you deal with rare event long tail items?
So one of the way we deal with this is by oversampling these rare images in the condensed data set, so that it hopefully remains in the condensed data set, so that when you fine tune the model, these samples will be continuously seen by the model.
Great. In approach number 3, are you changing the resolution for each head similar to YOLO?
A multi-scale approach is definitely possible, but that's not something that we are looking at right now. We think increasing data volume, finding ways to increase the trained data set is a more promising way to improve our models.
And do you think that generating synthetic data through image manipulation could help, or even using GANs to generate new images?
So in this approach, this dataset distillation approach, they are not using any GAN. They actually simply backpropagate. So they fix the weight and they basically backpropagate the images. And that's how they get these like synthetic examples. So it appears that in this paper that I mentioned here, they don't need to use a GAN, which is great. So because it's much easier to train if you don't use a GAN.
Great, thank you. All right, I'm not seeing any more questions. So thank you very much for joining us today. Again, our next Tech Talk will be on February 17th. You can find all the information for that event at scale.com/events. Felix, thank you so much for your time, and thank you everybody for joining us today. Have a great day.